Well, hello everyone, and welcome to Prep 34. So in this prep, we're going to be looking at hypothesis testing. And here's our first problem. This is called the furniture problem 2Z because it's going to be a two-sample Z test, and that'll make more sense as we go through. So a corporate manager of a major furniture outlet recently wanted to see if there was a difference in the dollar value of sales between the men and women he employs as sales associates. To research his hypothesis, he selected random samples of sales data. Sales data for men and women at various locations is shown here, and that's here off to the left. Assume the population standard deviation for men is 210 and for women is 245. At a significance level of 0.05 significance, can the manager conclude that the mean amount sold per day is larger for the women? Okay, so let's go ahead and write down what we know. So the case is going to be one-tailed right because we're testing to see if the women are selling more than men. The distribution here is a Z distribution. You know that, well, because I told you, but you also know it because we're given the standard deviation. And whenever you're given the standard deviation, that makes it a Z distribution as opposed to a T distribution. Okay, let's look at the sample size. So we're going to count the number of records that we have here for the men. So 40 records for the men, and for the women, and we have more records for the women, so 50 records for the women. Then let's get the mean, which is going to be the average here. And for the women, the average here. Okay, the expected variability, which is the standard deviation, is that was given in the problem. It's 210 for women and 245 for men. And now we're interested in the observed difference. So X bar women minus X bar men, and that is equal to women minus the men. All right, so we see that the difference that's observed from these two samples is 148, and our job is to figure out, well, is that sort of within normal limits of variability, or is that significant? And so let's go ahead and make our null hypothesis. The null hypothesis is always that there's no significant difference between the population mean for women and the population mean for men. And I want you to notice that the inference is about the population, not the samples. Obviously, the women in these two samples sold more, but we're trying to figure out, do the women overall sell more? And the alternative hypothesis is that the population mean for women is significantly greater than that for men. All right, now let's put this in pictures. So over here, let's look at the null hypothesis. The null hypothesis is that they're part of the same population. We'll call it the blue population. And that there's two samples here, and they're both inside the blue population. You know, there's a little wiggle room here. You know, they don't have to be the exact same amount. The means don't have to be exactly the same because there is random sampling variability between samples. If we discover that that's not true, then we go for the alternative hypothesis, which is that the women that are represented here by the dashed line actually belong to a different population. So the men would be here in the blue population, and the women would be over here in the pink population. So that's what we're trying to decide, which picture is actually true. All right, and in order to decide that, we need to calculate what's the standard error. So there's two things that we need. First, we need the expected mean difference. In other words, what do we expect to be true Well, we expect the two populations to be the same, right? So expected mean difference is 0. And then we need the expected variability, which is given by this square root function. So it's the square root of, for men, sigma squared divided by the number of men, plus, and then for women, sigma squared divided by the number of women. Okay, and that's our standard error, right? This number right here. This number is so important that we're going to actually give it its own little symbol. It looks like a ruler. And we're going to use this number to form the sampling distribution of the sample mean, which is what is over here, right? So what this is, this would be if you took like 1 million samples in here, right? Just 1 million different samples, and then plotted them, what would you expect the variability, the difference to be between the two samples, right? You're taking 1 million different pairs of samples, you're subtracting the means, and what are your expected difference? Obviously, most of the time, it's going to be around 0, because two samples from the same population should end up with kind of the same mean, or close to it. And as you get further and further away from 0, it means the samples are further and further away from each other, which is less and less likely. In our particular case, we're observing a difference of 148, which is way out here. So that looks a little suspicious. But let's keep going. So first, let's find out how many standard errors until we reach the boundary, right? The boundary where we would basically say, look, we're not in the same population. We're probably going to have to reject. So that's going to be based on our alpha, which is 0.05 or 5%. And now we're going to calculate our critical values. The critical values appear here on this second chart. So these two charts are actually really similar. These are the sample mean differences, and these are the sample mean differences standardized. So the difference between them is that the x-axis here actually has, the real differences in raw numbers between the different means. And down here, it has those same differences, this time expressed as z-scores. Okay, so critical value, the lower bound of the critical value is given by norm.s.inverse, and then it's going to be of this probability. But not exactly, because this would be the two-tailed example. We're going to do the two-tailed and then the one-tailed. So we'll divide by 2. There's our lower bound. And then for the upper bound, norm.s.inverse. And this will be 1 minus the probability divided by 2. All right, and we can actually do, because that's the sort of the right tail, we're going to do a similar thing over here, but this time we're going to give it all the probability. So it equals norm.s.inverse 1 minus all the probability, not divided by 2. And that's 1.64. And you can see these here, right? So this is the critical value, meaning that if we fall over here in the green region, we're going to reject the null hypothesis. All right, so let's see what actually happens. So we're going to calculate a z-score, which is going to be the observed difference divided by the expected variability. So observed difference is that 148. Expected variability is the standard error. So that's 3.10. All right, now this gives some more context. We already thought that it looked like an outlier over here. This is the same number expressed on the standardized scale. And as you can see here, we're clearly in the rejection region, right? And now we need to calculate the probability. You already get a glimpse of what it's going to be, but let's see if we can calculate the same number. So that's going to be equal to norm dot s dot dist of z, and then it's true because it's cumulative probability, but we're on the right tail, so this is going to give us the wrong number. It's going to give us the left tail. So we're going to take all of that and subtract it from 1. That gives that 0.10%. All right. So, could they, like, on a very, very, very strange off chance, have come from the same population? Maybe. But that seems so unlikely that we're going to reject the null hypothesis, because we've already set our criteria for rejection as, look, if there's less than a 5% chance that the two samples are from the same population, then we're going to actually say that they're from different populations. So the conclusion here is to reject the null, and the reason for that is that that percentage means samples probably come from different populations, and our interpretation is then if they're different populations, then the population mean for women is significantly greater than men. So going all the way back to this picture, we're effectively saying this is the true picture, that from different populations, and the population for women is greater than, further to the right, than for men. So you're rejecting the null. If you're wrong, what this would be which error type. Here you just have to memorize these. So this is a type 1 error, which is you reject the null hypothesis when it's actually true. So, like I said, maybe it could have happened, but we're willing to live with that. Okay, so if we reject the null, then the confidence interval will show the true difference between population means. In other words, we'd actually like to see where that population is for the women. Right? What is the true population mean? We can't say for sure, but we can give a range. So what we begin with is the observed difference between the samples. So let's go get that again. And then we subtract from that so minus the the critical value, the lower bound. Well, actually, we'll use the upper bound for both, so that we have the positive number since we're subtracting, so it all works out. So we're gonna subtract from that the critical value, the positive critical value, times the standard error. And then on the other end, we're going to take that value and add the positive two-tailed test upper limit times the standard error. All right, so this is our range. Let's go back to the original picture to see what it looks like. And what it looks like is this. This is the critical value lower bound. This is the confidence interval lower bound. This is the confidence interval upper bound. This is what we observed. So we're effectively saying that the population the difference between the populations. In other words, how much women sell more than men, right? And that, from a business standpoint, is really what we want to know, right? Could be anywhere in this range. They're at least selling $54 more than men, and it could be as high as $242. From our sample, it looked like the difference was $148, but again, that could be sampling error. So we could be anywhere in this range. What the true difference is between the two populations. And so that's important from a business standpoint too, because you don't want to just say, oh, well, this is what we observed in the two populations, so that really is the true difference. You don't know that. But you do know the true difference is between 54 and 242 at 95% probability, in other words, which is pretty good probability. And I think that is it for Prep 3-4. So congrats, and we'll see you in the next one.